Hi everyone, welcome back to PRAKASAM tutorials. In my previous video, we have discussed about concept of cross power density spectrum. Now here in this video, we are going to discuss about relationship between cross spectrum, cross power spectrum and cross correlation functions. Let capital X of t and capital Y of t be jointly wide sense stationary random process with the cross correlation functions are Rxy of tau and Ryx of tau, and their cross power spectral densities are Sxy of omega and Syx of omega. Then the cross spectral density of this pair of random process are defined by the Fourier transform of the cross correlation function. So that is Fourier transform of cross correlation function is equal to cross power spectral density. So the mathematical expressions, the cross correlation function and cross power spectral densities form a Fourier transform pair, and that mathematical expressions are Sxy of omega is equal Fourier transform of Rxy of tau, which is equal integral minus infinity to infinity Rxy of tau into e power minus j omega tau d tau, and its inverse Fourier transform is Rxy of tau is equal 1 by 2 pi integral minus infinity to infinity Sxy of omega e power j omega tau d omega. And this is the mathematical definition of Fourier transform of cross correlation function of the random process x of t and y of t. So similarly, the Fourier transform of cross correlation function of the random process y of t and x of t is given by or defined as Syx of omega is equal Fourier transform of Ryx of tau, which is equal to integral minus infinity to infinity Ryx of tau e power minus j omega tau d tau, and its inverse Fourier transform is Ryx of tau is equal f inverse of Syx of omega, which is equal 1 by 2 pi integral minus infinity to infinity Syx of omega e power j omega tau d omega. And this is the statement of the relationship between cross power spectral density and cross correlation function. Now coming to the proof, we know that xt of t and yt of t uh, are two signals, and their Fourier transforms are xt of omega and yt of omega. So the Fourier transform of the signals x of t and y of t are given by Fourier transform of xt of t is equal to xt of omega, which is equal integral minus capital T2 plus capital T xt of t e power minus j omega t dt. But the signal xt of t is equal to x of t over the finite interval, that is minus capital T2 plus capital T. So this equation is also written as integral minus capital T2 plus capital T x of t into e power minus j omega t dt. Similarly, the Fourier transform of the second signal, that is Fourier transform of yt of t is equal to yt of omega, and yt of t is the signal. That signal is considered as y of t for t is equal to minus capital T2 plus capital T. So the Fourier transform of yt of t is integral minus capital T to t y of t e power minus j omega t dt. And this is the definition of Fourier transform of the signals x of t and y of t. If we take the expected value and imposing the limits minus capital T2 plus capital T, we get. So, but we know that the expression of the cross power spectral density. The cross power spectral density expression is Sxy of omega is equal limit t tends to infinity 1 by 2t into expectation of xt conjugate of omega into yt of omega. So first calculate xt conjugate of omega into yt of omega, and this is the value of xt of omega, and this is the expression of the yt of omega. So now we want to calculate xt conjugate of omega and yt of omega. So in this expression, take conjugate on both sides. Xt conjugate of omega is equal RHS term whole conjugate. So RHS term whole conjugate means x conjugate of t into e power plus j omega t. E power minus j omega t whole conjugate is e power j omega t. So therefore, xt conjugate of omega into yt of omega is equal integral minus t to t x conjugate of t1 is considered as x of t1 since x conjugate of t1 is equal to x of t1 into e power j omega t1 dt1 into yt of omega integral minus capital T to t y of t2 e power minus j omega t2 d2. So that is equal RHS term of the above equation is xt conjugate of t xt conjugate of omega into yt of omega is equal integral minus t to t x of t1 dt1 into integral minus t to t y of t2. These two exponential terms e power j omega t1 into e power minus j omega t2 is written as e power minus j omega of t2 minus t1 dt2. So now here t1 and t2 are the dummy variables and x of t1 and x of t2 are the sample functions of the random process x of t and y of t. Now here capital X of t and capital Y of t are the two random process and with their sample functions are x of t1 and y of t2. X of t1 is the sample function of the random process x of t and y of t2 is the sample function of the random process y of t. And small t1 and small t2 are the dummy variables. So let us consider in this equation substituting small t1 is equal to t and t2 minus t1 is equal to tau. So RHS side of this equation, so T1 ranges are minus capital T2 plus capital T and T2 ranges are minus capital T2 plus capital T. Now here we are considering small t1 is equal to t and t2 minus t1 is equal to tau. So next calculate in this equation, okay, t1 is equal to t, differentiating with respect to t, dt1 is equal to dt. So differentiating this consideration with respect to tau, dt2 is equal to d tau. In this consideration, t1 is equal to t, substitute t1 ranges, we get small t ranges. In this expression, substitute t2 ranges, we get tau ranges. So next calculate the ranges of the small t and the ranges of the tau. So t1 is equal to t and substitute lower value of t1 that is minus capital T in this equation, then small t is equal to minus capital T and t1 is equal to plus capital T that is upper value of t1, then small t is equal to capital T. So substitute t1 ranges into this consideration. The ranges of the small t are minus capital T2 plus capital T. So T2 minus T1 is equal to tau, but T1 is equal to T, substitute in this equation. So T2 is equal to T plus tau. So in this consideration, substitute T2 ranges, then calculate tau ranges. If T2 is equal to minus capital tau, that is the lower value of T2, then tau is equal to minus capital T minus T. And T2 is equal to plus capital T, that is the upper value of T2, then tau is equal to capital T minus T. Okay, substituting all these considerations into this equation, RHS term of this equation, we get xt conjugate of omega into yt of omega is equal. So integral tau ranges are minus integral minus t minus small t to capital T minus t x of t1. So x of t1 is equal to t x of t dt1 is dt. Integral small t ranges are minus capital T2 plus capital T y of t2. So t2 is equal to t plus tau y of t plus tau e power minus j omega of t2 minus t1. So t2 minus t1 is tau. E power minus j omega tau t tau. So what is the definition of the cross power spectral density? The cross power spectral density definition is limit t tends to infinity expectation of ht conjugate of omega yt of omega by 2t. Okay. So in this equation, so taking on both side limits and also taking expectation and also taking 1 by 2t on both sides, we get the resultant expression is the LHS term is limit t tends to infinity expectation of xt conjugate of omega yt of omega divided by 2t is equal limit t tends to infinity 1 by 2t expectation of RHS term. Expectation of this RHS term. So now here in this integration applying the limit value, what is the limit value here? Capital T is equal to infinity. In this integration applying the limit value, the RHS term is we get limit t tends to infinity expectation of applying this first integration limit value integral minus infinity to infinity limit t tends to infinity 1 by 2t expectation 1 by 2t integral minus t to t. So applying the expectation into sample value of the random variable, that is expectation of x of t into y of t plus tau into dt into e power minus j omega tau d tau. So the RHS term of this equation can be arranged for convenient this one. So that is equal integral minus infinity to infinity limit t tends to infinity 1 by 2t integral minus capital T2 plus capital T. So expectation of x of t y of t plus tau is the cross correlation function of the random process x of t and y of t. So that is rxy of t comma t plus tau into dt into e power minus j omega tau d tau. So that is equal LHS term is definition of the cross power spectral density and it is denoted as Sxy of omega. Therefore, Sxy of omega is equal integral minus infinity to infinity C of Rxy of t comma t plus tau into e power minus j omega tau d tau, where C of Rxy of t comma t plus tau represents the time average of the cross correlation function, that is Rxy of t comma t plus tau, and it is given by the time average of the cross correlation function is C of Rxy of t comma t plus tau is equal limit t tends to infinity 1 by 2t integral minus capital T to t Rxy of t comma t plus tau. Okay, so now here in this equation, this within the bracket term is the time average of the cross correlation function, that is C of Rxy of t comma t plus tau. Next, when the random process are at least weights and stationary random process. So the condition of the at least weights and stationary random process condition is time average of the cross correlation function is equal to cross correlation function. So that is C of Rxy of t comma t plus tau is equal Rxy of tau. So applying the weights and stationary random process condition into this equation, we get the cross power spectral density expression is given by Sxy of omega is equal integral minus infinity to infinity Rxy of tau into e power minus j omega tau d tau. So this is the equation of Fourier transform of the cross correlation function of the random process x of t and y of t. And its inverse Fourier transform is Rxy of tau is equal F inverse of Sxy of omega is equal 1 by 2 pi integral minus infinity to infinity Sxy of omega e power j omega tau d omega. Okay, this is the relationship between cross correlation function and cross power spectrum density of the random process x of t and y of t.